All right, let's step beyond what we know, beyond the familiar, and gaze into the true cosmic ocean. For your entire life, you've probably imagined our solar system as a kind of cosmic island, right? Our sun, a blazing lighthouse, surrounded by its loyal planets, their moons, and a dusty, icy disk of comets and asteroids, all orbiting harmoniously. It's a neat, tidy picture, a backyard we understand. But what if I told you that our cosmic backyard isn't so isolated after all?
What if I told you that we're actually living right alongside a bustling, invisible interstellar highway, where cosmic wanderers from other star systems are constantly zipping past, sometimes right through our own little corner of the galaxy?
I want you to cast your mind back to October 2017. Imagine a team of astronomers meticulously scanning the night sky with the Pan-STARRS telescope in Hawaii. This isn't just any telescope. It's a behemoth designed to find things that move, to catch faint specks of light darting across the vastness. And on this particular night, they found something truly unprecedented, something that sent ripples of excitement and a good deal of head-scratching across the entire scientific community. They had discovered an object, initially designated A2017U1, that was moving too fast.
Not too fast for a rocket, but too fast to be gravitationally bound to our sun. Its trajectory wasn't an ellipse, like every planet, asteroid or comet we'd ever seen orbiting our star. No, this object was on a hyperbolic path, a cosmic slingshot that meant it had come from outside our solar system, made a quick pass by our sun, and was now accelerating out of our solar system, never to return. It was our first confirmed interstellar visitor.
They named it Oumuamua, a Hawaiian word meaning a messenger from afar arriving first. And what a messenger it was! Imagine trying to describe something you've never seen before. Oumuamua was baffling. It wasn't a fuzzy comet with a glowing tail, nor was it a typical potato-shaped asteroid. Instead, its brightness varied wildly, suggesting it was extremely elongated, perhaps cigar-shaped, or even a flat pancake-like object tumbling end over end through space. Its measurements were astounding, perhaps 400 meters long, but only 40 meters wide. And here's the kicker. It showed no visible coma, no gassy halo, no dusty tail, the very hallmarks of a comet. Yet, as it sped away from the sun, it exhibited a tiny, persistent push, a non-gravitational acceleration, almost as if it were subtly outgassing, but without any detectable gas. Scientists proposed everything from exotic hydrogen ice outgassing to the wilder idea of it being an alien probe. The truth, as always, was probably stranger and more mundane, a unique, ancient relic from another star system, unlike anything forged in our own. Then, just 2 years later, in August 2019, another discovery, this time by an amateur astronomer named Gennady Borisov. He spotted something else moving on a hyperbolic trajectory, confirming it was another interstellar visitor. This one, designated 2I Borisov, was different, very different. It was a comet, a beautiful, unmistakable comet,
complete with a fuzzy coma and a developing tail of gas and dust. Imagine the relief and excitement. Here was the confirmation. Oumuamua wasn't a fluke, and interstellar space wasn't just empty void. It was teeming with these cosmic vagabonds, and some of them looked just like the comets we know, made of rock, dust, and frozen volatiles like water, carbon monoxide, and methane. What does this mean? It means that throughout the galaxy, as star systems form, grow, and mature, they're constantly flinging material into the vast emptiness of interstellar space. Think of it like a cosmic game of billiards. Giant planets, like our Jupiter, gravitationally kick smaller, icy, and rocky bodies out of their home systems, sending them on journeys that can last millions, even billions of years. These ejected bodies achieve what we call escape velocity. They're moving so fast that the gravitational pull of their home star can no longer hold on to them. They become true interstellar wanderers, sailing silently through the dark, icy depths between the stars, carrying the primordial chemistry of their birth system across unimaginable distances. When these objects like Oumuamua and Borisov finally encounter our solar system, they're traveling at incredible speeds, often tens of kilometers per second relative to the Sun. They don't slow down to orbit, they just curve around our star for a brief moment, pulled by its immense gravity, and then slingshot out again, heading back into the great unknown. Their composition, revealed through spectroscopic analysis, essentially breaking down the light they reflect into a chemical fingerprint, tells us stories. Borisov, for instance, showed a chemical composition very similar to our own solar system's comets, suggesting that the building blocks of planetary systems might be quite universal across the galaxy. Oumuamua, with its mysterious lack of outgassing, hints at either a very different origin or a long, harsh journey that stripped it of its more volatile compounds. So, this interstellar highway isn't just a theoretical concept, it's real. We've seen the traffic, and it makes us wonder, what else is out there? What other exotic materials, what other cosmic stories are silently drifting towards us, waiting to be discovered? And this brings us to the very heart of our story. Because what if one of these interstellar wanderers, a true cosmic comet from another star, didn't just pass by? What if its path, after millions of years of solitary travel across the galaxy, brought it directly into our path? What if, say, an interstellar comet we'll call 3I Atlas, a hypothetical but entirely plausible behemoth of ice and rock, much like a larger, faster 2I Borisov, was discovered to be on a collision course with Earth? That's the scenario we're going to explore. The physics, the chemistry, the sheer, unimaginable scale of such an event. Welcome to the interstellar highway, where the fate of worlds might just depend on a visitor from beyond our wildest dreams. All right, so we've been talking about the vastness, the grandeur of our own cosmic backyard, the solar system. But now, I want you to shift your gaze, not just to the edge of our celestial neighborhood, but far, far beyond it. We're going to embark on a journey that begins not with a bang, but with a whisper of dust and ice, billions of years ago, in a star system utterly alien to our own. Imagine, if you will, another nascent star, a younger, wilder version of our Sun, just beginning to ignite in the heart of a swirling, flattened disk of gas and dust. This isn't just any dust. It's the cosmic detritus left over from the collapse of a colossal molecular cloud. Think of it as the ultimate cosmic construction site, a swirling, turbulent maelstrom where the very building blocks of planets, moons, and yes, comets are being forged. The temperatures vary wildly across this disk. Close to the fiery heart of the protostar, only refractory materials, tough silicates, metals, can withstand the intense heat, forming a region where rocky planets might eventually coalesce. But as you move further out, into the colder, darker reaches, something magical happens. The temperature drops below the snow line or ice line. This isn't a line you can see, but a critical thermodynamic boundary. Beyond this line, volatile compounds that were vaporized closer in, like water, methane, ammonia, and carbon dioxide, can freeze solid.
They don't just freeze, they coat the tiny silicate dust grains, forming icy mantles, turning mundane cosmic dust into glittering, primordial snowballs.
Now, these minuscule dust grains, some no larger than a smoke particle, are dancing in this disk. They're constantly bumping into each other, nudged by the gentle, persistent pressure of the gas. At first, it's a slow-motion ballet. Electrostatic forces, like the static cling you feel after pulling clothes from a dryer, start to pull these tiny particles together. They stick. Slowly, painstakingly, they grow, from microns to millimeters, then to centimeters. It's a process called coagulation.
Think of it like a cosmic snowball fight, but in slow motion, where every tiny flake that touches another sticks. As they grow, gravity, that fundamental sculptor of the cosmos, begins to take over. These centimeter-sized pebbles, now called pebble accretion, start to gravitationally attract more dust and ice, sweeping up material like a cosmic vacuum cleaner. They grow into kilometer-sized planetesimals, the true architectural bricks of planetary systems.
Some of these planetesimals, born beyond that crucial snow line, are rich in ice, a frozen time capsule of the original molecular cloud.
These icy planetesimals, the ancestors of comets, are born in the chaotic outer reaches of their home star system. Our own solar system, for instance, has its Kuiper belt and its Oort cloud, vast reservoirs of these icy wanderers. But not all of them are destined to remain in their birth system. Oh no, this is where the true drama begins. As giant planets, the Jupiters and Neptunes of these alien worlds grow and migrate. Their immense gravitational influence becomes a cosmic wrecking ball. Imagine a colossal game of billiards, but on a scale that beggars belief. These massive planets, in their orbital dance, can slingshot smaller, icy bodies. A close gravitational encounter isn't just a gentle nudge, it's a violent acceleration. These icy planetesimals are flung inwards, outwards, their orbits becoming wild, eccentric ellipses. Some might crash into the nascent star, vaporizing in a spectacular flash. Others might collide with other growing planets, delivering their precious cargo of water and organics. But a significant number, a vast, untold multitude, get the ultimate cosmic boot. They achieve escape velocity. That's the critical speed an object needs to break free from the gravitational pull of its parent star, to become truly unbound. It's like launching a rocket from Earth,
But instead of just reaching orbit, it accelerates so powerfully that it leaves the solar system entirely, never to return. These ejected icy bodies, these cosmic refugees, are then cast out into the cold, dark, unforgiving vacuum of interstellar space. They become interstellar comets or interstellar objects, true cosmic nomads, adrift in the vast ocean between star systems. They are moving at incredible speeds, not just relative to their home star, but relative to every star they encounter. They are travelers, carrying the chemical fingerprints of their birth system, a silent message from a distant cosmic shore. And it's not just one or two. Scientists estimate that billions, perhaps trillions, of these icy wanderers are ejected from every forming planetary system. The cosmos is teeming with them, a silent, unseen armada of icy messengers. Our own solar system has likely ejected countless such objects, and in turn it has captured some too, perhaps adding them to our own Oort cloud. But we're interested in the ones that simply pass through, briefly gracing our presence before continuing their endless journey across the galaxy. They are the ultimate time capsules, preserving the pristine, primordial chemistry of their birth nebula, untouched by the ravages of a star's intense radiation or the thermal processing within a forming planetary system. Then, one day, we saw one. In 2019, astronomers spotted a fuzzy, faint object showing signs of cometary activity, meaning it was shedding gas and dust as it warmed up. Its trajectory was unmistakable. It was hyperbolic, meaning it wasn't orbiting our sun. It was just passing through, never to return. We named it 3I/Atlas. The 3I stands for Third Interstellar Object Discovered, and Atlas comes from the Atlas Survey Telescope in Hawaii that first spotted it. This wasn't just a rock, it was a comet, an icy wanderer from another star system, a true cosmic nomad, a direct product of the very violent, chaotic, yet utterly beautiful process of planet formation we just described. It was a tangible, icy handshake from a stellar neighbor, a fleeting glimpse into the history of another world, billions of years in the making, now streaking across our sky at breathtaking speed. And its journey, its very existence, tells us a profound story about how common these interstellar travelers truly are. All right, let's talk about visitors. Not the kind that knock on your door, but the kind that traverse the unimaginable distances between stars, arriving in our solar system like cosmic tumbleweeds. For millennia, we've gazed up at the stars, wondering what might be out there. We've imagined aliens, distant civilizations, and exotic worlds. But what we didn't fully anticipate, until very recently, was that pieces of those distant star systems would come to us. And they did. Not as sleek, chrome-plated spacecraft, but as humble, silent wanderers, carrying secrets from beyond. I want you to cast your mind back to October 19, 2017. Imagine a team of astronomers in Hawaii peering through the Pan-STARRS telescope. They weren't looking for anything extraordinary, just routine sky surveys. But then, a faint speck of light appeared on their screens. It was moving, fast, unusually fast. So fast, in fact, that its trajectory was hyperbolic. Now, what does that mean? It means it wasn't gravitationally bound to our sun. It wasn't an asteroid from our asteroid belt, or a comet from the distant Oort cloud,
orbiting our star in a predictable ellipse.
No. This object was on a one-way trip, slingshotting around our sun and heading back out into the interstellar void, never to return. This was an object from another star system.
And that, my friends, was our first confirmed interstellar visitor. It was named 1I/Oumuamua. The I stands for interstellar, and Oumuamua is Hawaiian for a messenger from afar reaching out first. And what a messenger it was! As astronomers scrambled to observe it before it vanished, Oumuamua revealed itself to be utterly bizarre. First, its shape. While we couldn't get a direct image, its brightness varied wildly as it tumbled, suggesting it was incredibly elongated, perhaps like a cosmic cigar or a pancake. Imagine something perhaps 400 meters long, but only 40 meters wide.
That's a ratio unlike anything we'd ever seen in our own solar system.
But here's where it got truly perplexing. As it sped away from the sun, it seemed to be accelerating just a tiny bit, more than gravity alone could explain. For comets, this non-gravitational acceleration is normal. As they get close to the sun, ice heats up and turns directly into gas, a process called sublimation, creating jets that act like tiny thrusters, pushing the comet along. This is what creates the beautiful tail we associate with comets. But Oumuamua showed no signs of a tail, no visible coma, no dust, no gas. It was just
A rock, or so it seemed, silently accelerating. What could be causing it?
Scientists proposed various theories. Maybe it was releasing tiny, invisible jets of gas that we couldn't detect. Perhaps it was made of a highly volatile ice, like hydrogen ice or nitrogen ice, which would sublimate without creating a visible dust trail, an alien probe. The alien hypothesis, while exciting, quickly lost traction among mainstream scientists.
The observed acceleration was tiny, and while mysterious, there were still plausible natural explanations, even if they required exotic compositions. Oumuamua was a true enigma, a silent, dark shard from another star, offering tantalizing clues but no easy answers about its home system. It left us with more questions than answers, a cosmic riddle that continues to spark debate.
Then, less than 2 years later, in August 2019, another visitor arrived. This time, it was spotted by amateur astronomer Gennady Borisov from Crimea. And this one, designated 2I/Borisov, was different. As it approached the sun, there was no doubt it was a comet. It developed a clear, unmistakable coma, the fuzzy atmosphere of gas and dust surrounding the nucleus, and a distinct tail. This was a classic comet, just like the ones we've studied for centuries, but with that same telltale hyperbolic trajectory. It, too, was an interstellar traveler.
Borisov was a gift to astronomers because, unlike Oumuamua, it behaved like a familiar object. We could study its composition. Telescopes around the world, from the Hubble Space Telescope to ground-based observatories, turned their gaze towards it. And what did they find? They found water ice, just like our solar system's comets. They found carbon monoxide, hydrogen cyanide, the chemical building blocks often seen in our own comets. But there were subtle differences. For instance, Borisov had unusually high levels of carbon monoxide compared to typical solar system comets. This suggests it might have formed in a colder region of its home star system, or that its parent star was different,
leading to a different chemical environment during planet formation. Think about the implications of these two visitors. Oumuamua, a mysterious, possibly icy cigar-shaped object, silently accelerating. Borisov, a textbook comet, complete with a fuzzy head and a streaming tail. Both arrived from the vast, dark spaces between stars. Both were ejected from their birth systems, perhaps during violent planetary formation events, flung out into the galactic wilderness, drifting for millions, if not billions of years, until they happened upon our sun's gravitational embrace. These objects are more than just interesting astronomical curiosities. They are literal fragments of other star systems, offering us a direct, albeit small, sample of the raw materials from which other planets, and perhaps other life, might have formed. They are the closest thing we've had to first contact, not with intelligent beings, but with the physical matter of another star's domain. They tell us that the process of planetary system formation, which often involves ejecting large numbers of icy and rocky bodies, is a universal phenomenon.
Our solar system isn't unique in scattering its debris.
And they serve as a powerful reminder of the dynamic, interconnected nature of the cosmos. The universe isn't just a collection of isolated star systems, it's a vast ocean where objects constantly drift, collide, and interact across unimaginable scales. Oumuamua and Borisov were just the first two we spotted. How many more are out there, silently cruising through our cosmic neighborhood, waiting to be discovered? The sky is far from empty, and the universe continues to surprise us with its boundless complexity and its unexpected guests.
All right, let's dive back into the cosmic ocean, shall we? You've heard about these interstellar wanderers, these ghostly travelers from beyond our sun's gravitational embrace. But how, you might ask, do we even spot them? How do we catch a glimpse of a tiny, dark object hurtling through the unimaginable vastness of space, often against the glare of a million stars? It's like finding a single unlit firefly in a stadium full of flashing lights, while you're blindfolded and the firefly is moving at supersonic speed.
It's a truly monumental challenge, a cosmic game of hide and seek, where the stakes are, well, potentially planetary. For centuries, our view of the cosmos was limited. We saw the bright planets, the steady stars, the occasional streaking comet or meteor, but the truly small, truly dark, truly distant objects remained elusive. The breakthrough, as with so many revolutions in astronomy, came with technology, bigger telescopes, more sensitive detectors, and, crucially, the power of computation. We needed to stop just looking and start hunting. Imagine for a moment you're a cosmic detective. Your suspects are small, dark, and they don't want to be found. They don't emit their own light. They merely reflect the faint glow of the sun, and only if they happen to be close enough. Most of their journey through interstellar space is in absolute darkness, a cold, silent drift. It's only when they begin to approach a star like our sun that they get a chance to shine, however dimly. And even then, they're often tiny, a few hundred meters or a few kilometers across at most.
That's a needle in a haystack, friends. A cosmic needle in an infinite haystack.
The real hunt began in earnest with wide-field survey telescopes. Think of them as vast digital eyes that continuously sweep the sky, taking snapshot after snapshot, night after night. One of the most famous of these is the Pan-STARRS telescope in Hawaii. Pan-STARRS isn't designed to stare intently at one tiny patch of sky. Instead, it's built to cover enormous swathes, systematically mapping everything it sees. It takes images of the same regions of the sky multiple times over several nights. And then, here's the clever bit, it compares those images.
What are we looking for? Not a star, because stars are fixed relative to each other over short timescales. Not a distant galaxy, which also appears stationary. We're looking for something that moves, something that shifts its position against the background of the static stars. This apparent motion is called proper motion. If an object is moving fast enough or close enough, it will appear to jump from one position to another between successive images. The computer algorithms, tireless and precise, are trained to spot these tiny shifts, these faint blips of light that don't belong to the celestial furniture.
Once a candidate is flagged, a tiny moving speck, other telescopes are called in. This is where the detective work truly intensifies. We need to determine its orbit. Is it looping around the Sun, a familiar solar system resident, or is it on a trajectory that's truly alien? To figure this out, astronomers employ a technique called astrometry, precisely measuring the object's position over time. By tracking its path over days, weeks, even months, we can calculate its trajectory, its speed, and its eccentricity. And this, my friends, is the smoking gun for an interstellar visitor.
Solar system objects, bound by the Sun's gravity, follow elliptical orbits. They're like loyal pets on a very long leash. But an interstellar object, it's coming in from deep space, unbound. It will follow what we call a hyperbolic trajectory. Imagine a stone skipping across a pond. It comes in, curves slightly as it interacts with the water, and then shoots off again, never to return. That's a hyperbolic orbit. It means its velocity is so high, its energy so great, that the Sun's gravity isn't strong enough to capture it. It just slingshots around and heads back out into the void. When we calculate an orbital eccentricity greater than 1, we know we've found an interstellar interloper. But the hunt doesn't stop there. Once we've confirmed its interstellar nature, we want to know what it is. Is it a rocky asteroid, a frozen comet, or something even stranger? This is where the physics of light truly shines, quite literally. We use photometry to measure its brightness and how that brightness changes. If an object is tumbling end over end or has an irregular shape, its reflected light will flicker as different parts of its surface catch the sunlight. This light curve can tell us about its rotation period and even give us clues about its shape, as we saw with the infamous Oumuamua, which had an incredibly elongated, cigar-like profile. And then there's spectroscopy. This is where we truly unlock the chemical secrets of these cosmic wanderers. Imagine taking the sunlight reflected off the object and passing it through a prism, splitting it into its constituent colors, just like a rainbow. But it's not a perfect rainbow. There will be dark lines, like missing pieces, or bright lines, like sudden flashes of color, at very specific wavelengths. These are the spectral fingerprints of elements and molecules. Each element, each compound, absorbs or emits light at unique wavelengths. By analyzing these lines,
we can determine the chemical composition of the object's surface, or, if it's a comet, the gases and dust in its coma, the fuzzy atmosphere it develops as it approaches the sun, and its ices begin to sublimate.
For example, if we see lines indicating water vapor, carbon monoxide, or diatomic carbon, we know we're looking at a comet, a dirty snowball, as they're often called. If we see signatures of silicates, iron, or other rocky materials, we might be looking at an asteroid. The presence of complex organic molecules, like tholins, those reddish, tar-like substances found on some outer solar system bodies, tells us about the ancient, irradiated chemistry of its home star system.
And the overall color, the reddening of its surface, can hint at billions of years of exposure to cosmic rays, scorching its outer layers.
This is precisely how we characterized objects like Oumuamua, the first confirmed interstellar visitor in 2017. Pan-STARRS spotted it. Follow-up observations quickly revealed its hyperbolic orbit. Its bizarre light curve suggested an extreme elongated shape, and spectroscopy showed a reddish, carbon-rich surface, but crucially, no coma, no outgassing. It behaved more like a rocky asteroid than a comet, yet its non-gravitational acceleration hinted at some form of outgassing that remained undetected. A true enigma.
Then, in 2019, came 2I Borisov, another interstellar comet. This time, there was no doubt. Discovered by amateur astronomer Gennady Borisov, it quickly developed a distinct coma and tail as it neared the Sun. Spectroscopy confirmed it was a comet, rich in water ice, cyanogen, and diatomic carbon. Very similar to our own solar system comets, but with subtle differences in its chemical ratios, a clear sign of a different birthplace. Borisov was the cosmic reassurance we needed. Interstellar comets are out there, and they're not all cigar-shaped mysteries. And now, our subject, 3I/Atlas. Imagine the same process unfolding, but with an even greater sense of urgency. Our vast network of telescopes, from Pan-STARRS to the soon-to-be operational Vera C. Rubin Observatory, are constantly scanning. One night, a faint moving speck is detected. Its motion is tracked. The orbital calculations are run. And then, the chilling confirmation, a hyperbolic trajectory. This object, 3I/Atlas, is not from around here. It's a visitor, and its path, as we will discover, is bringing it uncomfortably close to home.
The hunt is on, not just for scientific curiosity, but for potential planetary defense. The ability to spot these unseen wanderers, to characterize them, and to predict their trajectories is paramount. Because in this vast, dynamic universe, sometimes what we don't see can truly hurt us. The next generation of telescopes, like the Vera C. Rubin Observatory, with its incredibly wide field of view and rapid survey capabilities, promises to discover thousands more of these objects, both local and interstellar. We are, at last, truly beginning to see the unseen.
All right, everyone, settle in. Because today, we're going to meet a ghost. Not a spooky, spectral ghost, but a cosmic one. A traveler from beyond the stars, carrying secrets from places we can only dream of. I want you to imagine, for a moment, a celestial wanderer, a true alien in every sense of the word. We're talking about an interstellar comet, a specific one we'll call 3I/Atlas.
Now, you've heard me talk about comets before, Those dirty snowballs from the outer reaches of our own solar system. But 3I/Atlas, it's different. It's not from here. Its story began light years away, perhaps orbiting a star long dead, or maybe even forming in the cold, dark embrace of an interstellar cloud, never knowing the warmth of a sun until it entered our cosmic neighborhood. This isn't just a comet, it's a messenger, a time capsule, and a potential harbinger of incredible change.
When we first spotted 3I Atlas, it was just a faint smudge in the sky, hurtling through the black. But its speed, its impossible speed, was the first clue. It wasn't just fast, it was too fast to be gravitationally bound to our sun. Its trajectory was a hyperbolic curve, not the elliptical path of our local comets. Think of it like a stone skipping across the surface of a pond. It enters, interacts briefly, and then slingshots away, never to return. That hyperbolic path, that slingshot maneuver, is the unmistakable signature of an interstellar object.
It tells us unequivocally that 3I Atlas is merely passing through, a transient visitor in our cosmic backyard. Now, let's unpack this cosmic visitor piece by piece. What is 3I/Atlas made of? Well, like all comets, it's primarily a giant, irregular chunk of ice and dust, what astronomers lovingly call a dirty snowball. But its interstellar origin makes its composition incredibly intriguing. Imagine a nucleus, perhaps a few kilometers across, a dark, rocky heart encasing a treasure trove of frozen volatiles. We're talking about water ice, of course, but also frozen carbon dioxide, carbon monoxide, methane, ammonia, and even more complex organic molecules like methanol and formaldehyde. These aren't just random ingredients. They are the building blocks of life, preserved in deep freeze for billions of years, locked away in the comet's nucleus. When 3I/Atlas gets close enough to our sun, some of these volatile ices begin to sublimate, turning directly from solid to gas, skipping the liquid phase entirely. This creates the comet's glowing coma, that vast, fuzzy envelope of gas and dust, sometimes hundreds of thousands of kilometers wide, and its iconic tail, stretching millions of kilometers behind it, pushed by the solar wind and radiation pressure. The chemistry of 3I Atlas is where it truly gets fascinating. Because it formed outside our solar system, its chemical fingerprint could be subtly or even dramatically different from our local comets. It might contain isotopes of elements in ratios we rarely see here, or perhaps unique, complex organic molecules that hint at different stellar nurseries or planetary formation processes. It's like finding an ancient artifact from a lost civilization. The materials, the craftsmanship, the very design all speak of a different origin, a different history. Analyzing the light from its coma and tail, scientists can identify these chemical signatures, reading the cosmic story etched in its very being. But what if this magnificent, ancient traveler, this interstellar ghost, were to collide with Earth? It's a terrifying thought, a cosmic lottery we desperately hope never to win. Let's explore 3 potential scenarios, escalating in their devastating impact. Scenario 1. The atmospheric burst. Imagine 3I/Atlas, a smaller fragment perhaps, or even a larger one that breaks apart under the immense stress of Earth's gravity and atmospheric pressure, screaming into our atmosphere at tens of kilometers per second. It wouldn't even touch the ground. Instead, the sheer friction and pressure of its hypersonic entry would cause it to explode high above the surface, an airburst of unimaginable power. Think about the Tunguska event in 1908, where a relatively small object, likely a stony asteroid or a fragment of a comet, detonated over Siberia with the force of 10-15 megatons of TNT, flattening 2,000 square kilometers of forest. Now scale that up for a potentially larger, faster interstellar comet fragment. The resulting shockwave would be catastrophic, capable of leveling entire cities or vast swathes of land. Buildings would crumble, trees would be incinerated, and a massive fireball would briefly ignite the sky. The immediate aftermath would be widespread destruction, followed by localized atmospheric disturbances, perhaps a temporary cooling due to dust, but not a global catastrophe. It would be a regional disaster, a stark reminder of our cosmic vulnerability, but humanity as a whole would endure. Scenario 2. The regional devastator. Now, let's imagine a more substantial chunk of 3I Atlas, perhaps a few hundred meters across, making it through the atmosphere largely intact and slamming into Earth. If it hits land, the impact would carve out a crater many kilometers wide and hundreds of meters deep, instantly vaporizing everything within a vast radius. The energy released would be equivalent to thousands of nuclear bombs detonating simultaneously. A colossal earthquake would ripple across continents, and a superheated blast wave would incinerate everything in its path for hundreds of kilometers. But what if it hits the ocean? The consequences would be equally terrifying. A massive displacement of water would generate colossal tsunamis, perhaps hundreds of meters high, surging across entire ocean basins, inundating coastal cities and low-lying regions across the globe. The immediate loss of life would be staggering, and the economic and social infrastructure of entire nations would collapse. Dust and aerosols injected into the atmosphere would lead to a period of global cooling, disrupting agriculture and causing widespread famine. But again, likely not an extinction-level event for humanity, though civilization would be profoundly altered. Scenario 3. The extinction event. This is the nightmare scenario. If the core of 3I Atlas, a kilometer or more in diameter, were to strike Earth, it would be an event of truly global, catastrophic proportions. The impact itself would unleash an energy equivalent to billions of megatons of TNT. The immediate effects would be unimaginable, a firestorm igniting across continents as superheated ejecta re-enters the atmosphere, triggering massive wildfires. A colossal dust cloud, composed of pulverized rock and vaporized comet material, would be ejected high into the stratosphere, encircling the entire planet within days. This dust cloud would block out the sun, plunging Earth into an impact winter that could last for years or even decades. Photosynthesis would largely cease, collapsing food webs from the bottom up. Global temperatures would plummet, acid rain would fall, poisoning ecosystems, and the very chemistry of our oceans would be altered. This scenario would lead to mass extinctions on a scale not seen since the dinosaurs vanished 66 million years ago. Humanity's survival would be precarious at best, pushed to the brink, with only scattered remnants potentially enduring a radically transformed, hostile planet.
These scenarios, while hypothetical, underscore the profound importance of understanding and tracking these cosmic wanderers. 3-Eye Atlas, a silent, ancient ghost from beyond our sun, reminds us that the universe is a vast, dynamic place, and sometimes those distant stories can come knocking right on our doorstep. It's a humbling thought, isn't it? To know that the fate of worlds can sometimes hinge on the path of a single icy snowball from another star. All right, let's dive into a question that has haunted humanity's imagination for millennia. What if something from beyond our solar system, a true cosmic wanderer, actually hits us? We've talked about these interstellar visitors, like the fascinating 3-Eye Atlas, a comet that just zipped through our neighborhood, a fleeting ghost from another star system. Now, I want you to truly feel the weight of this possibility. Is an impact inevitable? What would it even mean? First, let's confront the sheer mind-boggling scale of space. It's vast beyond human comprehension. Think about the tiny target that is Earth, a blue marble hurtling through an enormous cosmic shooting gallery. The odds of any specific object, say a particular interstellar comet, hitting our planet are astronomically, almost impossibly small. The universe is mostly empty space, and even our solar system, with all its planets and asteroids, is mostly empty space. It's like trying to hit a specific grain of sand on a beach with another grain of sand fired blindly from miles away. But here's the kicker. While the odds for one specific object are tiny, there are billions upon billions of objects out there. Our solar system alone is teeming with countless asteroids and comets, remnants from its formation. And now we know, thanks to discoveries like Oumuamua and 3-Eye Atlas, that our solar system is regularly traversed by objects born around other stars. These are the true cosmic nomads, flung out from their home systems by gravitational slingshots, traveling for millions, even billions of years through the cold, dark interstellar void. They are moving at incredible speeds, often far faster than anything native to our solar system, because they aren't bound by our sun's gravity. They just pass through on a hyperbolic trajectory, a one-way ticket. So while the individual odds are small, the sheer number of potential projectiles means the risk, however remote, is always there. Earth has been hit countless times in its 4.5 billion year history. Remember the Chicxulub impactor, the one that ended the reign of the dinosaurs 66 million years ago? That was a rocky asteroid, perhaps 10 to 15 kilometers across, a resident of our own solar system. And the Tunguska event in 1908, a much smaller object, likely a stony asteroid or a fragment of a comet, that exploded in the atmosphere over Siberia with the force of about 10 to 15 megatons of TNT, flattening 2,000 square kilometers of forest. These events, though rare on human timescales, are a stark reminder of our planet's cosmic vulnerability. Now, let's imagine an interstellar comet. Let's call it Atlas X, following in the footsteps of 3-Eye Atlas, but this time its trajectory is a bullseye. What would happen? The impact scenario depends critically on three things: the object's size, its composition, and its velocity. Interstellar objects, as I mentioned, often have much higher velocities than solar system objects. This means their kinetic energy, the energy of motion, is exponentially greater. Even a smaller interstellar object could pack the punch of a much larger solar system one, simply because of its speed. Let's break it down into three chilling scenarios. Scenario 1, the atmospheric annihilation, a regional catastrophe. Imagine Atlas X is a relatively small interstellar wanderer, perhaps a few hundred meters across, roughly the size of a few football fields, and let's say it's composed mostly of ice and dust, like a typical comet. As it plunges into Earth's atmosphere at a staggering velocity, say 60 to 80 kilometers per second, far faster than any bullet,
The friction with the air becomes immense. The pressure on its leading face builds, the temperature skyrockets. It doesn't even need to hit the ground. Before it can, the incredible stress tears it apart. The comet fragments, and then, a few tens of kilometers above the surface, it detonates in a colossal airburst. Think of a super Tunguska event. The air itself, superheated to millions of degrees Celsius, expands outwards in a devastating shockwave. If this happened over a populated area, the immediate effect would be catastrophic. Buildings would be leveled, trees would be incinerated and flattened for hundreds, even thousands of square kilometers. The sheer concussive force would be enough to cause widespread internal injuries and death. The intense thermal radiation, a flash hotter than the surface of the sun, would ignite widespread firestorms, turning forests and cities into infernos. The chemistry of the atmosphere would be temporarily altered. Enormous amounts of nitrogen oxides would form from the superheated air, leading to acid rain that could damage ecosystems for years. But importantly, while utterly devastating regionally, this event would likely not cause a global extinction. Humanity would survive, but with a profound scar and a terrifying lesson. Scenario 2. The ocean's fury, a coastal apocalypse. Now let's scale up. Imagine Atlas X is a kilometer or two in diameter, a substantial chunk of ice and rock, still moving at that terrifying interstellar velocity. And this time, it smashes into the deep ocean. The impact would be beyond comprehension. The object would penetrate the water with such force that it would essentially create a temporary void, exposing the seafloor for a fraction of a second. Then, an enormous column of water, superheated steam and vaporized rock would erupt upwards miles into the atmosphere, creating a massive transient crater in the ocean. The immediate effect would be a series of colossal tsunamis, unlike anything ever recorded in human history. Imagine waves not just tens of meters high, but potentially hundreds of meters high, radiating outwards across entire ocean basins. These waves would utterly devastate coastal regions worldwide, sweeping away cities, infrastructure, and entire ecosystems for many kilometers inland. The sheer volume of water displacement would be staggering. Furthermore, the massive injection of superheated steam and salt aerosols into the stratosphere could have significant, though perhaps temporary, global climate effects. The salt particles would act as cloud condensation nuclei, potentially altering weather patterns, while the steam could contribute to a temporary greenhouse effect. Marine life would be decimated in the impact zone, and the global disruption of ocean currents could lead to long-term ecological changes. Again, humanity might survive, but the world would be irreversibly changed, with a vast portion of its population and infrastructure wiped out. Scenario 3. The global winter, an extinction event. Finally, let's consider the truly terrifying prospect. Atlas X is a formidable beast, say 5 to 10 kilometers across, a true planetary killer, much like the one that ended the dinosaurs. And this time, it smashes into a continental landmass. The impact would be instantaneous, brutal, and globally catastrophic. The sheer kinetic energy released would be equivalent to billions of atomic bombs detonating simultaneously. The object would vaporize on contact, along with many kilometers of Earth's crust, forming an enormous crater, easily 100 kilometers wide and many kilometers deep. The ground would literally melt and vaporize. An enormous plume of superheated rock vapor, dust, and gases would be ejected high above the atmosphere, some even escaping Earth's gravity. A massive shockwave would rip across the planet, triggering earthquakes of unprecedented magnitude and volcanic eruptions worldwide. The immediate thermal pulse from the impact would ignite global firestorms, turning continents into raging infernos. Soot and aerosols from these fires, combined with the fine dust and sulfate aerosols from the impact itself, would quickly encircle the globe. This thick, dark veil would block out sunlight for months, perhaps years. Photosynthesis would largely cease, leading to a collapse of food chains. Global temperatures would plummet, ushering in a prolonged impact winter. Acid rain, far more severe than in our first scenario, would drench the planet, poisoning soils and oceans. Most complex life forms, including a significant portion of humanity, would perish from starvation, cold, and the poisoned environment. This is the scenario that truly resets the clock for life on Earth. So, while the odds of any specific interstellar comet hitting us are incredibly low, the universe is a vast place, and it's constantly sending us visitors. The scientific community is diligently working on planetary defense, scanning the skies, tracking objects, and developing strategies to mitigate such a threat should one ever loom on the horizon. Because even though the odds are small, the stakes, as you can now imagine, are utterly immense.
All right, let's dive into a scenario that, while exhilarating, would also be a profound moment for all of humanity. Imagine, if you will, the year is, well, let's just say it's soon. very soon. You wake up one morning, and the news isn't about politics or the stock market. It's about a celestial visitor, a ghost from another star, hurtling towards our cosmic neighborhood. This isn't just any comet. This is 3I Atlas, our fictional yet scientifically plausible interstellar wanderer. Remember Oumuamua and 2I Borisov, those real-life trailblazers that first showed us objects from other star systems are indeed passing through our own? Well, 3I Atlas is like them, but with a twist that sends shivers down the spines of astronomers worldwide. It was first spotted, perhaps, by one of our automated sky survey telescopes, maybe the actual Atlas system, or Pan-STARRS, tirelessly scanning the heavens. A tiny, faint smudge of light, moving across the background stars at an utterly bewildering speed. Not in the familiar elliptical path of our solar system's comets, but on a distinctly hyperbolic trajectory. That's the giveaway, the cosmic fingerprint of an object that doesn't belong to our sun, an object merely passing through, never to return. Initial calculations, made in those frantic first hours and days, are concerning. The trajectory, still uncertain due to limited observational data, suggests it's going to be close, too close for comfort. As more telescopes around the globe are pointed at this rapidly approaching interloper, as weeks turn into a month, the data sharpens, the error bars shrink, and then the announcement comes, simultaneously terrifying and breathtaking. 3I Atlas will miss Earth, but only just. We're talking a near miss of epic, unprecedented proportions. Now, what does a near miss mean in the vast, empty canvas of space? It means it's not going to hit us, thank goodness, but it's going to pass closer than any object of its size in recorded human history. Imagine it screaming past us, perhaps within 1 million kilometers. That's roughly 2.5 times the distance to the moon. Or maybe, to amp up the spectacle even further, it dips inside the moon's orbit, a mere few 100,000 kilometers away. At these distances, the gravitational tug of Earth and Moon might slightly perturb its path, but certainly not enough to drag it into an impact, nor would it significantly alter our orbit. We're talking about a cosmic ballet, not a collision. Let's talk about the physics of this flyby. 3I Atlas isn't dawdling, it's hurtling through space at speeds upwards of 50 or 60 kilometers per second. To give you some perspective, that's fast enough to cross the continental United States in under 2 minutes. Our own Earth orbits the Sun at about 30 kilometers per second. So this thing is moving with incredible kinetic energy, a veritable cannonball from another star system. As it plunges towards the inner solar system, it's not just its speed that's remarkable, it's the transformation it undergoes. See, 3I Atlas, like most comets, is a dirty snowball, a frozen relic of its distant birth, composed of water ice, frozen carbon dioxide, methane, ammonia, and a mishmash of rocky dust and complex organic molecules. For eons, it drifted in the frigid darkness between stars, a silent, inert chunk of primordial matter. But as it crosses the frost line of our solar system, that imaginary boundary where the sun's heat becomes intense enough to vaporize volatile ices, it begins to awaken. The sun's radiation, a relentless barrage of photons, starts to warm its surface. The ices don't melt, they sublimate, turning directly from solid to gas, bypassing the liquid phase entirely. This process releases vast quantities of gas and dust, forming a fuzzy, glowing envelope around the nucleus called a coma. And then the tail. Oh, the tail. This is where the true spectacle begins. The solar wind, a stream of charged particles constantly emanating from the sun, pushes these gases and dust away from the comet, creating those iconic luminous streamers. You'd see 2 main types of tails. First, the dust tail, composed of tiny, sand to pebble-sized particles, gently pushed by the pressure of sunlight itself. This tail often appears broad, yellowish-white, and curves gracefully behind the comet, tracing its orbital path. Second, the iron tail, made of ionized gases, molecules that have lost or gained electrons due to interactions with solar ultraviolet radiation and the solar wind. These charged particles are swept directly away from the sun by the magnetic fields embedded in the solar wind, forming a straight, narrow, often bluish-tinged tail that points directly away from our star. The chemistry here is fascinating. Spectral analysis would reveal the signatures of carbon monoxide ions, nitrogen ions, hydroxyl radicals, all glowing under the sun's intense gaze.
As 3i Atlas makes its closest approach, it wouldn't just be a faint smudge, it would become a truly magnificent sight, brighter than any comet in living memory, perhaps even visible in broad daylight against the blue sky. A dazzling streak of light with a shimmering ethereal tail stretching for tens of millions of kilometers. Imagine standing outside, looking up, and seeing this cosmic apparition, a vibrant slash across the heavens. It would be a global phenomenon, uniting humanity in a shared moment of awe and wonder, and perhaps a touch of primal fear. Telescopes, both professional and amateur, would be trained on it, collecting an unprecedented wealth of data. Every spectrometer, every camera, every radar dish would be focused on this interstellar visitor, trying to unlock its secrets. Scientists would be in a frenzy, analyzing the light reflected and emitted by the coma and tail. Spectrometry would be our primary tool, allowing us to identify the specific chemical elements and molecules present, the very building blocks of another star system. What kind of water ice does it have? Is it enriched in certain isotopes? What organic compounds can we detect? This isn't just a pretty light show, it's a direct sample return mission without the mission. It's a pristine chunk of primordial matter, untouched by the billions of years of processing that our own solar systems have undergone, offering clues to the birthplace of other stars and planets. This near miss would be a profound wake-up call, a visceral reminder of the dynamic, ever-changing cosmos we inhabit. It would inspire a new generation of scientists and astronomers, fuel new space missions, perhaps even accelerate plans to develop technologies for intercepting and studying future interstellar objects up close. As 3i Atlas recedes, its glory fading into the blackness from which it came, it leaves us not with destruction, but with an immeasurable gift: knowledge, wonder, and a renewed sense of our place in the grand cosmic tapestry. It would be a moment etched into the collective memory of humanity, a testament to the beauty and the subtle power of the universe.
All right, take a deep breath. We've talked about the impossible miss, the cosmic sigh of relief. But what if our luck, our cosmic lottery ticket, didn't quite hit the jackpot? What if 3i Atlas, this icy, ancient wanderer, didn't just sail past, a silent specter in the night? What if it did find us, but not with the full, devastating force of a planet killer? I want you to imagine a different kind of horror, one that carves a scar across continents, an apocalypse for millions, but not for every single living thing on Earth. This is our second scenario, the regional cataclysm. Let's say 3i Atlas, this colossal, roughly 10-kilometer wide behemoth, isn't a single monolithic chunk of ice and rock. Like many comets, it's a fragile, loosely aggregated structure, sometimes prone to shedding pieces. Or perhaps, and this is a chilling thought, another smaller interstellar object, a sibling in speed but not in size, is the one that crosses our path. For this scenario, let's picture an object maybe a kilometer or two across, still gargantuan, still traveling at an unthinkable 50 kilometers per second, or roughly 112,000 miles per hour. That's fast enough to cross the continental United States in under a minute. And this time, it's not a direct hit on a major landmass. No, the cosmic dice roll lands it in the vast, deep blue. Let's place it, for the sake of terrifying illustration, somewhere in the North Atlantic, perhaps a few hundred kilometers off the eastern seaboard of North America, or maybe west of Europe, in the deep abyssal plain. The approach would be breathtaking, terrifying. For days, then hours, it would grow from a faint, fast-moving star to an undeniable beacon in the sky, a searing point of light. As it plunges into our atmosphere, the friction would be unimaginable. The air in its path, compressed and superheated, would glow with an intensity that would turn night into a blinding, searing day across thousands of miles. It wouldn't just burn, it would literally vaporize the air in front of it, creating a plasma sheath hotter than the surface of the sun. The roar, if you could even call it that, would be an infrasonic rumble felt in your bones long before any sound waves reached your ears, followed by a supersonic shockwave tearing through the atmosphere, flattening forests and structures as if they were made of paper,
hundreds or even thousands of kilometers from the actual impact site. Then, the ocean. Imagine a mountain traveling at hypersonic speeds, slamming into the fabric of our world. The kinetic energy released would be staggering, measured not in tons of TNT, but in hundreds of gigatons. To put that in perspective, the largest nuclear weapon ever detonated, the Tsar bomber, was about 50 megatons. We're talking about an energy release thousands of times greater than that. The immediate impact would be an instantaneous, colossal explosion of water. The ocean in that precise spot would cease to be liquid. It would be vaporized, turned into superheated steam in an instant, creating a cavity miles wide and deep. This cavity would briefly expose the seafloor, only for the surrounding water to collapse back in, creating an immense, towering central peak of water that would then surge outward in concentric rings. This isn't just a splash, it's a planetary-scale punch to the liquid heart of Earth. The primary killer in this scenario? The tsunami. Oh, not just a tsunami, but the mother of all tsunamis, a wave unlike anything humanity has ever witnessed. Imagine a wall of water, not just 10 or 20 meters high, but potentially hundreds of meters high at its origin, propagating outwards. The speed of a tsunami in the deep ocean is incredible, often comparable to a jet airliner, hundreds of miles per hour. As this monumental wave travels across the ocean, it might not look like a towering wall in the deep open water, but rather a subtle yet incredibly long rise in sea level. But as it approaches coastlines, as the seafloor shallows, all that energy, all that water is compressed and forced upwards. Picture the eastern seaboard of North America or the western coasts of Europe and Africa. Hours after impact, the sky might still be hazy from atmospheric debris, but the real terror would arrive from the sea. A wave perhaps 100 meters, 200 meters, or even more in vertical run-up height would crash ashore. It wouldn't just flood cities, it would erase them. Coastal cities like New York, Boston, London, Lisbon, Casablanca, utterly annihilated. Skyscrapers would be scoured clean of their outer facades, then shattered and collapsed under the sheer, unyielding force of billions of tons of water. The wave would surge inland for tens, perhaps hundreds of kilometers, depending on the topography, carrying with it the debris of entire civilizations, transforming fertile plains into saltwater deserts, rendering vast tracts of land uninhabitable for generations due to salt contamination.
All right. So we've talked about the near miss, the atmospheric breakup, the scenarios where we get a warning, where we might even survive with some regional devastation. But now, I need you to brace yourselves, because we're going to explore the darkest, most terrifying possibility, the direct hit, the extinction-level event. This isn't just about a bad day. This is about the end of a world as we know it, perhaps even the end of humanity's story. I want you to imagine, if you can, 3I Atlas, this interstellar rogue, perhaps 10 kilometers across, a colossal chunk of ice and rock, screaming through the void at a breathtaking 70 kilometers per second. That's not a car on the highway. That's faster than any bullet, faster than the Voyager spacecraft. It's an almost unimaginable velocity. And it's not just passing by, not skimming the atmosphere. This time, our calculations are tragically precise. Its trajectory leads directly to impact. There would be no warning, not really, not in the way you might think. Even if astronomers spotted it, the time between detection and impact could be weeks, maybe months at best. But for most of us, the first sign would be the last. Because as 3I Atlas slams into our atmosphere, it wouldn't just burn up. Oh no, the air in front of it would compress with such unimaginable force that it would instantly superheat to millions of degrees, creating a colossal incandescent plasma shield. Think of it, the very air itself exploding in a flash brighter than 1,000 suns, visible across an entire hemisphere. This isn't just a meteor shower, This is the sky itself tearing open.
Then comes the impact. Let's say it hits land, a continental plate perhaps. The kinetic energy released would be mind-boggling, truly astronomical. We're talking about the equivalent of billions of Hiroshima bombs detonating simultaneously. The asteroid itself, in that instant, wouldn't just hit the ground, it would vaporize the ground. It would create a transient cavity, a colossal hole in the Earth's crust, miles deep and tens of miles wide, almost instantaneously. The rock and soil beneath it would be subjected to pressures so immense they would behave like a fluid flowing outwards, then rebounding, creating a central peak within the nascent crater. The immediate aftermath? A searing, incandescent plume of superheated rock vapor, dust and gases would erupt upwards, punching through the atmosphere and into space. This isn't just a cloud, it's a column of incandescent fury carrying billions of tons of pulverized Earth material with it. And as this plume collapses, an enormous spherical shockwave would ripple outwards from the impact site, flattening everything in its path for hundreds, even thousands of miles. Cities would be annihilated, forests incinerated, mountains pulverized. The ground beneath you, even thousands of miles away, would heave and buckle with global-scale earthquakes, magnitudes far beyond anything recorded in human history. If it hit the ocean, the tsunami generated would be a continent-spanning wall of water, scouring coastlines clean.
But the true global catastrophe begins with the ejecta. All those billions of tons of superheated material launched into the upper atmosphere and beyond. Gravity pulls it back down, and as this incandescent rain of molten rock and dust re-enters the atmosphere, it heats the air to temperatures so extreme that the entire planet would be engulfed in a global firestorm. Imagine the sky not with clouds, but with a glowing orange-red canopy of re-entering debris. Everything flammable, every forest, every building, every blade of dry grass would spontaneously combust.
The world would become an oven, a planetary inferno, burning from pole to pole. And then, the darkness. The fires would send colossal amounts of soot and smoke into the atmosphere, joining the fine dust from the impact itself. This dense, opaque veil would shroud the entire planet, blocking out the sun for months, perhaps even years. This is what scientists call an impact winter. Photosynthesis, the very engine of life on Earth, would grind to a halt. Plants would die, crops would fail, and the base of every food chain would collapse. Temperatures would plummet, not just a little, but dramatically, turning much of the Earth into a frozen, twilight wasteland. But wait, there's more. The chemistry of this nightmare scenario is equally devastating. The intense heat of the impact and the re-entering ejecta would cause atmospheric nitrogen and oxygen to combine, forming nitric oxides. These would then react with atmospheric water vapor, raining down as highly corrosive nitric acid, making already scarce potable water toxic and further devastating plant life. If the comet hit a sulfur-rich area, or if it contained significant sulfur itself, we'd also see massive amounts of sulfur dioxide released, leading to sulfuric acid rain, another layer of chemical destruction.
The oceans, too, would suffer immensely. As the atmosphere becomes saturated with carbon dioxide from the burning world and various acidic compounds, these would dissolve into the surface waters, leading to widespread ocean acidification. Marine organisms, particularly those with calcium carbonate shells or skeletons, would struggle or die, collapsing marine food webs. The very building blocks of ocean life, from microscopic plankton to coral reefs, would be under siege.
This isn't just a reset button, it's a hard wipe. The KPG extinction event, the one that wiped out the dinosaurs 66 million years ago, was caused by an asteroid estimated to be around 10-15 kilometers. It plunged the world into an impact winter, triggered global fires, and led to the demise of 75% of all species. An interstellar comet like 3I Atlas, potentially similar in size, but with a much higher velocity due to its interstellar origin, could deliver an even more catastrophic punch, potentially pushing the planet beyond recovery for complex life.
Humanity's fate in such a scenario? It would be a struggle for survival on a scale unimaginable. Those who survived the initial blast, the earthquakes, the tsunamis, and the global firestorm would then face a world plunged into darkness, bitter cold, and poisoned air and water. Food would be non-existent. Society would disintegrate. Small, isolated pockets of humanity might cling to existence in underground bunkers or remote, protected areas, but they would emerge into a world utterly transformed, a barren, lifeless landscape, a stark reminder of the cosmic lottery we'd lost.
It's a vision that underscores the incredible fragility of our existence, a chilling testament to the power of the universe, and a stark reminder that sometimes the greatest threats come from the deepest, darkest reaches of space. This is the ultimate cosmic crossing, a collision that ends worlds. And while it's a terrifying thought, understanding these extreme possibilities helps us appreciate the delicate balance that allows life to thrive here on Earth, and motivates us to keep our eyes on the skies, ever vigilant. All right, I want you to imagine something truly terrifying, something that keeps scientists around the globe awake at night, not with fear, but with determination. We've talked about these cosmic wanderers, these objects from beyond our solar system, Oumuamua, Borisov. But what if one of them wasn't just a fleeting visitor? What if one, perhaps a hypothetical cousin to the real 3I Atlas, a rogue comet or asteroid, was on a direct collision course with Earth? And what if we only had, say, a few months, or even just weeks to react? This isn't science fiction anymore. It's a very real, albeit low probability, threat. When we talk about an interstellar object like 3I Atlas, we're discussing something that could be moving at truly staggering speeds, perhaps 50, 60, even 70 kilometers per second relative to the Sun, which means its speed relative to Earth could be equally immense. This isn't like a slow-moving inner solar system asteroid. This is a cosmic bullet. Let's explore 3 distinct scenarios, each painting a grim but scientifically plausible picture of what could unfold, depending on the nature of this hypothetical interstellar interloper. Scenario 1. The direct hit. An extinction event revisited.
Imagine our hypothetical 3-eye atlas, a rocky iron body perhaps 5 kilometers in diameter, hurtling through the vacuum. Its trajectory is locked. There's no escaping it. As it punches through our atmosphere, the friction alone would be unimaginable. The air in front of it would superheat, glowing with plasma, screaming towards the surface. The impact itself would be over in a blink, but its consequences would echo for millennia. The kinetic energy released would be equivalent to billions of Hiroshima bombs detonating simultaneously.
Picture the Chicxulub impactor, the one that ended the reign of the dinosaurs, but perhaps even more energetic due to the interstellar object's higher velocity. At the point of impact, whether land or shallow ocean, a colossal crater would form, hundreds of kilometers wide and many kilometers deep, almost instantaneously. The shockwave would flatten everything for thousands of kilometers, pulverizing rocks, vaporizing water, and liquefying vast swathes of the Earth's crust. But that's just the immediate blast. The real killer would be the ejector, a colossal plume of superheated rock and dust, vaporized impactor material, and atmospheric gases would rocket skyward, punching through the atmosphere and even into space before falling back down. As these incandescent projectiles re-entered the atmosphere across the entire planet, they would heat the air to oven-like temperatures, igniting global wildfires. Forests, grasslands, cities, all would erupt into flame. The soot and smoke from these fires, combined with the fine dust from the impact itself, would be lofted high into the stratosphere, forming a dense, impenetrable shroud. This isn't just a cloudy day. This is a perpetual night, a planetary blackout that could last for years. Photosynthesis, the very foundation of most life on Earth, would grind to a halt. We'd enter an impact winter, temperatures plummeting globally, crops failing, and ecosystems collapsing. The chemistry of the atmosphere would be fundamentally altered. If the impact occurred on sulfur-rich crust, vast quantities of sulfur dioxide would be injected, leading to widespread sulfuric acid rain, further devastating land and ocean life. This, my friends, is the classic mass extinction scenario, played out in real time. Scenario 2. The Ocean Strike. Tsunami Cataclysm. Now, let's adjust our scenario. What if our hypothetical 3-eye atlas, still a multi-kilometer behemoth, slams into the deep ocean? The initial impact would still be devastating. A temporary cavity, tens of kilometers across, would open up in the water, exposing the seafloor for a fleeting moment. A colossal plume of superheated steam and water vapor, mixed with pulverized rock, would erupt into the atmosphere, potentially carrying massive amounts of water vapor high into the stratosphere, where it could also affect global climate patterns. But the most immediate and widespread horror would be the tsunamis. Not just large waves, but mega tsunamis. As the water rushed back into the impact cavity, it would rebound, sending out an initial wave that could be kilometers high near the impact site. This wall of water would then propagate across entire ocean basins. Imagine waves, still hundreds of meters tall, slamming into coastlines thousands of kilometers away, inundating vast stretches of land, wiping away coastal cities, ecosystems, and infrastructure as if they were made of matchsticks. The sheer force of the water would scour the land clean, reshaping continents. Beyond the physical destruction, the chemistry of the oceans would suffer. The massive disruption could lead to localized upwellings of deep anoxic waters, impacting marine life. The atmospheric injection of steam and other volatiles could temporarily alter weather patterns, and the long-term effects of ocean acidification from increased atmospheric CO2 from fires or impact-related outgassing would further stress marine ecosystems already reeling from the physical shock. Scenario 3. The atmospheric breakup. A global airburst. Finally, let's consider a slightly less dire, but still catastrophic possibility. What if our interstellar visitor is smaller, perhaps a few hundred meters across, or maybe it's a more fragile, icy comet that grazes the atmosphere at a shallow angle? Instead of a surface impact, we might witness an atmospheric breakup, a phenomenon known as an airburst. As the object slams into the denser layers of the atmosphere at hypersonic speeds, it would experience immense aerodynamic pressure. Even a rocky body could fragment, but an icy comet would vaporize and explode with astounding force. The most famous, albeit much smaller, historical example is the Tunguska event in 1908, where an object estimated to be 100 meters wide detonated over Siberia, flattening 2,000 square kilometers of forest. Or the Chelyabinsk meteor in 2013, which was only about 20 meters across, but still produced a shockwave that injured over 1,000 people. Now, scale that up to a multi-hundred-meter interstellar object. The energy released would be colossal, detonating tens of kilometers above the surface. There would be no crater, but the blast wave would be devastating. Picture an invisible hammer slamming down on the Earth. Cities would be leveled, infrastructure shattered, and forests flattened for thousands of square kilometers. The thermal pulse, an intense flash of heat from the superheated air, would cause widespread burns and ignite fires over a vast area. The chemistry here is also critical. The extreme temperatures generated by the airburst would cause atmospheric nitrogen and oxygen to combine, forming vast quantities of nitrogen oxides. These compounds would then react with water vapor to form nitric acid, leading to widespread acid rain that would damage ecosystems and structures. Furthermore, these nitrogen oxides could deplete the ozone layer, leaving the Earth vulnerable to increased ultraviolet radiation for years. Shielding our home. The imperative of planetary defense. These scenarios, as terrifying as they are not inevitable. They are hypothetical, designed to underscore the vital importance of what we call planetary defense. For decades, scientists have been diligently scanning the skies, cataloging near-Earth objects, NEOs, asteroids and comets whose orbits bring them close to our planet. Projects like Pan-STARRS, the Atlas system, and soon the Vera C. Rubin Observatory are our sentinels, our first line of defense, constantly searching for any celestial body that might pose a threat. But detecting an interstellar object, especially one moving so fast and appearing from an unexpected direction, is incredibly challenging. Early detection is paramount. If we have years or even a decade before a potential impact, our options expand dramatically. We are not talking about sending Bruce Willis to detonate a nuclear bomb in a Hollywood movie, though nuclear options are considered a last resort for very large, very late detection threats. Instead, the preferred methods involve more subtle yet effective techniques.
One is the kinetic impactor, a spacecraft designed to intentionally crash into the object, altering its velocity ever so slightly. A tiny nudge, applied far enough in advance, can change a collision course into a near miss. NASA's DART mission, which successfully demonstrated this concept by impacting the asteroid Dimorphos, proved this technology is viable.
Another concept is the gravity tractor, where a spacecraft flies alongside the object for an extended period, using its own minuscule gravitational pull to gently tug the object off course. These are the sophisticated, science-backed solutions we're developing.
The threat of an interstellar wanderer hitting Earth is real, though thankfully rare. But the stakes are literally everything. Our continued vigilance, our investment in space-based telescopes, and our development of planetary defense technologies are not just about protecting property or infrastructure. They are about safeguarding life itself, about ensuring humanity's long-term future among the stars. It's a testament to our ingenuity and our collective will to survive, to learn, and to thrive in this magnificent, yet sometimes perilous cosmos.
All right, so we've journeyed through the vastness of space, contemplating the incredible journey of an interstellar wanderer like 3I Atlas, a cosmic snow cannon hurtling through the void. We've imagined its trajectory, felt the chill of its potential approach. But now, let's confront the unthinkable. What if, despite our best efforts, despite all the science and vigilance, this magnificent, destructive ice ball were to strike our home? It's a terrifying thought, a scenario ripped from the pages of science fiction. Yet, the Earth has faced such impacts before, countless times over billions of years. And each time, our resilient planet has found a way to recover, to rebuild, to reawaken life from the ashes. Today, we're not just going to imagine the devastation. We're going to explore Earth's incredible capacity for healing, for rebirth, in the face of truly cosmic trauma. We'll look at 3 distinct scenarios, each progressively more catastrophic, yet each ultimately demonstrating the profound, enduring power of our world. First, let's consider a scenario that, while devastating, might spare us the absolute worst: an atmospheric airburst. Imagine 3I Atlas, a giant snowball perhaps a few hundred meters across, screaming through Earth's atmosphere at a mind-boggling speed, maybe 50 or 60 kilometers per second. This isn't just fast, it's an incomprehensible velocity that turns air into a solid wall. The sheer kinetic energy, the energy of its motion, is so immense that the atmosphere itself can't withstand it. Instead of hitting the ground, the comet fragments and explodes high above the surface, perhaps 10 to 20 kilometers up, in a colossal airburst. Think of the Tunguska event in Siberia in 1908, but amplified 1,000-fold. The physics here is brutal. The comet's rapid deceleration generates an astronomical amount of heat and pressure. The icy body, already under immense stress, vaporizes almost instantaneously in a superheated plasma fireball, releasing an energy equivalent to hundreds or even thousands of megatons of TNT. The immediate consequence, a blinding flash, a searing thermal pulse that ignites everything flammable over a vast radius. Forests explode into flame, dry vegetation instantly combusts. Then comes the shockwave, a truly monstrous wall of compressed air, expanding outwards at supersonic speeds. It flattens buildings, snaps trees like twigs, and creates an atmospheric overpressure capable of collapsing lungs. This isn't a regional earthquake, it's a regional atmospheric earthquake. The chemistry of such an event is equally profound. The intense heat in the fireball superheats the air, causing atmospheric nitrogen and oxygen to combine, forming vast quantities of nitrogen oxides. These oxides then react with water vapor to create nitric acid, which precipitates as a chilling, corrosive acid rain over a wide area. This sudden influx of acid can acidify lakes, damage plant life, and strip nutrients from soils. Furthermore, the shockwave and thermal pulse can temporarily deplete the ozone layer in the immediate vicinity, allowing a surge of harmful ultraviolet radiation to reach the surface. But here's the kicker for this scenario. Because there's no direct ground impact, there's no massive crater, no global dust veil blocking the sun for years. The atmosphere, though temporarily scarred, begins its self-cleansing process relatively quickly.
Winds disperse the nitrogen oxides, rain washes the acids from the sky. Ecosystems, though utterly destroyed at ground zero, begin the slow, inexorable process of ecological succession. Pioneer species colonize the scorched earth, life finds a foothold, and within decades nature begins to reclaim the scars. Humanity, though reeling from regional devastation, would survive, and the planet's global systems would largely remain intact. Now, let's escalate. What if 3I Atlas, still a multi-hundred-meter behemoth, slams directly into one of Earth's vast oceans? The physics of an oceanic impact is a terrifying ballet of water and rock. The comet, at its incredible velocity, doesn't just splash, it excavates a temporary cavity in the ocean floor, pushing aside cubic kilometers of water with unimaginable force. The immediate result is a colossal steam plume, a superheated column of water vapor and pulverized seabed material that erupts miles into the sky, punching through the stratosphere and potentially reaching the mesosphere. This steam, rich in sulfurs if it hits a continental shelf or an area with sulfate-rich sediments, would then condense and spread globally, forming a veil of sulfuric acid mist that encircles the planet. But before that, the displaced water collapses back into the cavity, creating a series of truly monstrous tsunamis, perhaps hundreds of meters high, radiating outwards across entire ocean basins. These aren't your typical earthquake tsunamis, these are walls of water capable of scouring coastlines clean across continents, devastating cities thousands of miles from the impact site. The chemistry of this scenario is more globally impactful. The massive injection of water vapor and sulfates into the upper atmosphere would trigger an impact winter. The sulfate aerosols, tiny reflective particles, would scatter incoming sunlight back into space, causing global temperatures to plummet for months, perhaps even years. Photosynthesis, the very engine of life, would be severely hampered, leading to a collapse in food chains, from phytoplankton in the oceans to forests on land. The oceans themselves would suffer. The initial shockwave and subsequent mixing could cause local anoxia, oxygen depletion, leading to widespread marine die-offs. The acid rain from the atmospheric sulfates would also slowly acidify surface waters, further stressing marine ecosystems, particularly those with calcium carbonate shells or skeletons, like corals. Yet, even in this dire scenario, Earth possesses profound resilience. The oceans are vast, dynamic systems. Over decades to centuries, global ocean currents would slowly mix and dilute the acidic waters, bringing fresh oxygen and re-establishing chemical equilibrium. The atmospheric aerosols, though persistent, would eventually be washed out by rain, allowing sunlight to return. Life in the deep sea, insulated from the immediate atmospheric and surface ocean changes, would act as a refuge, a biological seed bank from which new life could slowly, painstakingly recolonize the devastated surface waters. It would be a long, difficult recovery, marked by significant extinctions, but the planet itself and life upon it would endure. Now, for the ultimate challenge, what if 3I Atlas, a truly massive interstellar object, say kilometers in diameter, strikes directly into a continental landmass? This is the planet-killer scenario, the kind of event that brings about mass extinctions on a global scale. The physics is almost impossible to comprehend. The impact would create an enormous crater, perhaps tens or even hundreds of kilometers across, instantaneously vaporizing bedrock and sending seismic shockwaves rippling through the entire planet, causing global earthquakes and volcanic eruptions. A massive ejector curtain, composed of superheated rock and dust, would be blasted into space, only to re-enter the atmosphere globally, igniting the atmosphere and raining down incandescent debris. This would trigger global firestorms, turning vast swathes of land into an inferno. The chemistry here is devastating and long-lasting. The sheer volume of dust and soot injected into the atmosphere would create a perpetual twilight, plunging the Earth into a prolonged impact winter far more severe and long-lasting than an oceanic strike. Photosynthesis, the very engine of life, would largely cease for years, collapsing nearly all surface food webs. If the impact site were rich in carbonates like limestone, the vaporization would release colossal amounts of carbon dioxide, potentially leading to a long-term greenhouse effect after the initial cooling phase, creating a wildly fluctuating climate. The atmosphere would be choked with sulfur oxides from vaporized rocks, leading to truly apocalyptic acid rain that would strip soils, acidify remaining bodies of water, and dissolve exposed calcium carbonate structures. Ocean anoxia would become widespread, turning vast stretches of the deep ocean into lifeless zones. This is an extinction-level event, no doubt about it. Most complex life on the surface would perish, but here's the profound truth. Earth itself is not so easily defeated. Deep beneath the surface, in the hydrothermal vents of the ocean floor, in the subterranean aquifers, in the cracks and pores of the deep crust, life would persist. Extremophiles, organisms thriving in conditions we consider utterly hostile, would become the planet's inheritors. Geologically, the Earth would slowly, inexorably heal its wound. Plate tectonics, the planet's grand engine of renewal, would over millions of years recycle the crust, bury the crater, and reshape continents. Volcanic outgassing would slowly re-equilibrate the atmosphere, and from the surviving pockets of life, evolution would begin anew. It would take tens of millions of years, perhaps even hundreds of millions, for complex ecosystems to re-emerge and diversify, for a new biosphere to flourish. the Earth would be a different world, but it would be a living world, a testament to the ultimate resilience of our planet. So, while the threat of an interstellar comet is real and the potential devastation immense, remember this: our Earth is a survivor. It has faced cosmic challenges before, and it carries within it the seeds of its own and life's eternal rebirth.
All right, let's cast our gaze even further out, beyond the familiar dance of planets and asteroids in our own solar system. I want you to imagine for a moment an object that doesn't belong here. Not something born from the same swirling nebula of gas and dust that gave rise to our sun and its planetary children. No, I'm talking about a true wanderer, a cosmic vagabond, ejected from another star system entirely. These are the interstellar objects, and in recent years we've actually met a couple of them. Remember Oumuamua, that oddly shaped visitor, or Comet Borisov, a more traditional icy wanderer? They were just passing through, brief encounters, but they opened our eyes to a universe teeming with such travelers. Today, I want us to consider a hypothetical, yet scientifically plausible scenario. Let's imagine another such visitor, a comet we'll call 3I Atlas. And let's say, by the most astronomically improbable stroke of cosmic bad luck, this interstellar comet is on a collision course with Earth. What would that even look like? What would it feel like? Let's dive deep into 3 terrifying yet illuminating possibilities. First, let's consider a scenario where 3I Atlas, perhaps a kilometer or 2 across, doesn't hit us head-on. Instead, it breaks apart high in our atmosphere, or perhaps a significant fragment grazes us. Think of it like a cosmic bullet shattering before it hits its target. As this massive chunk of ice, dust, and rock, a relic from an alien solar system, plunges into our atmosphere at speeds upwards of 60 kilometers per second, or about 134,000 miles per hour, the air in front of it compresses and heats up to incandescent temperatures. We're talking tens of thousands of degrees Celsius, turning the comet's surface into a superheated plasma. This isn't just friction, it's a colossal compression wave. The comet, made largely of volatile ices like water, carbon dioxide, and methane, would begin to ablate furiously, shedding layers as it vaporizes. If it's a grazing blow, or if it breaks up due to the immense stresses, the bulk of its mass might continue past Earth, but not without leaving a devastating mark. The energy released by such an event, even if it's just an airburst, would be staggering. Picture the Tunguska event of 1908 in Siberia, where an object estimated to be only 50 to 100 meters across flattened 2,000 square kilometers of forest. Now multiply that energy by 100 or even 1,000 for a kilometer-sized fragment. The shockwave alone would be catastrophic, capable of leveling cities and creating hurricane-force winds across entire regions. The sky would light up with a brilliance rivaling the sun, followed by a deafening roar that would travel for thousands of miles. Locally, buildings would be pulverized, trees snapped like twigs, and anything flammable would likely ignite from the intense thermal pulse. The chemistry of our upper atmosphere would briefly be altered, with vast quantities of superheated steam and cometary gases injected, perhaps leading to localized changes in weather patterns for weeks or months. But crucially, for life globally, this scenario, while devastating locally, wouldn't be an extinction-level event. It would be a profound scar, a stark reminder of our cosmic vulnerability, but not the end of the story for humanity. Now let's escalate. What if a substantial portion of 3I Atlas, say a half-kilometer wide fragment, doesn't break up in the atmosphere, but instead plunges directly into one of our vast oceans? Our planet is 71% water, so this is a highly probable outcome. Imagine the sheer, unimaginable kinetic energy of this object, moving at hypersonic speeds, slamming into the deep blue. The impact would create an instant colossal cavity in the ocean, displacing an unfathomable volume of water. This isn't just a splash, it's an explosion, a momentary void in the sea, followed by a violent rebound. The water, propelled upwards, would create a towering plume of steam and superheated water vapor mixed with pulverized oceanic crust and cometary material rocketing miles into the stratosphere. This plume would inject vast amounts of water vapor, a potent greenhouse gas, along with aerosols like sulfur compounds from the ocean floor, into the upper atmosphere.
The immediate, terrifying consequence would be a series of monstrous tsunamis radiating outwards from the impact site. These weren't your typical earthquake-generated tsunamis. These would be mega tsunamis, potentially hundreds of meters high near the impact, capable of inundating coastal regions across entire continents. Cities along seaboards would be utterly annihilated, scoured clean by walls of water carrying debris and sediment far inland. The sheer force would reshape coastlines, trigger widespread seismic activity, and potentially even volcanic eruptions in tectonically unstable areas. Globally, the massive injection of steam and aerosols into the atmosphere would have a complex two-pronged effect on climate. Initially, the reflective aerosols might cause a brief cooling period, blocking sunlight. But the long-term effect of increased water vapor, a potent greenhouse gas, could lead to a significant warming trend, potentially disrupting global weather patterns and agricultural cycles for years. Marine life, especially along the coasts, would suffer catastrophic losses. This scenario would be a global catastrophe, a profound reshaping of our planet's environment, pushing many species, including our own, to the brink. But again, complete extinction of all life, while possible in the long term due to climate shifts, wouldn't be an immediate certainty. But what if the full, unadulterated mass of 3I Atlas, perhaps a 2-kilometer-wide icy behemoth, slammed directly into a continental landmass? This is the doomsday scenario, the kind of event that fundamentally rewrites the story of life on Earth. The impact would be beyond human comprehension. The kinetic energy released would be equivalent to billions of tons of TNT, far exceeding the combined destructive power of every nuclear weapon ever built. The comet would excavate a colossal crater, perhaps 30 to 40 kilometers across, instantly vaporizing rock and sending a superheated plume of pulverized earth and cometary material, along with superheated air, screaming into space. Think of the Chicxulub impact 66 million years ago, the event that wiped out the non-avian dinosaurs. This would be similar, perhaps even larger. The immediate aftermath would be a seismic shockwave of unimaginable power, triggering earthquakes globally, potentially tearing apart fault lines and igniting volcanic eruptions worldwide. A vast global ejecta blanket of incandescent rock and dust would rain back down through the atmosphere, heating the air to oven-like temperatures and igniting global fire forests. Every forest, every patch of dry vegetation would burst into flames. The skies would fill with soot, dust and aerosols, sulfur dioxide, nitric oxides, and fine particulate matter, blocking out the sun for months, perhaps even years. This is the dreaded impact winter, a period of prolonged darkness and freezing temperatures, even at the equator. Photosynthesis, the very foundation of most food webs, would grind to a halt. Acid rain, formed as atmospheric water reacts with nitric oxides from the superheated air and sulfur from the vaporized rock, would poison fresh water sources and acidify the oceans, devastating marine ecosystems. The chemistry of the entire planet would be thrown into chaos. Life as we know it would face its ultimate test. Only the most resilient, the most adaptable, those in sheltered environments or with incredibly slow metabolisms would have a chance to survive. This is the ultimate cosmic reset button, an event that doesn't just reshape the world, but fundamentally redefines the trajectory of evolution for millions of years to come. It's a sobering thought, isn't it? That a tiny speck of ice and rock, hurled across unimaginable distances from another star, could hold such power over the destiny of an entire world. It reminds us that our planet and the life it harbors is not an isolated experiment, but an active participant in a vast, dynamic, and sometimes violent cosmos. The story of life on Earth is inextricably linked to these cosmic crossings, both the gentle rain of everyday micrometeorites and the catastrophic hammer blows that punctuate geological time.
All right, my fellow cosmic explorers. We've journeyed through the birth of the universe, the dance of galaxies, the lives and deaths of stars, and even the mysterious dark components that weave the fabric of reality. We've peered into black holes, imagined alien worlds, and understood the incredible forces that shape everything around us. But now, as we reach the culmination of our adventure, I want us to turn our gaze back to our own home, Earth, and consider a possibility that reminds us just how dynamic and surprising the cosmos truly is. I want you to imagine a solitary wanderer, a frozen relic from another star system, hurtling through the vast emptiness of interstellar space. Not a star, not a planet, but a comet, an interstellar comet. We've actually seen a few of these, like Oumuamua and Borisov, but let's focus on a hypothetical one, perhaps one like 3I/Atlas, if it were on a collision course with our pale blue dot.
What if this cosmic interloper, born in the frigid nurseries around a distant sun, were to cross paths with Earth? What would that look like? Let's explore 3 terrifying, yet scientifically grounded scenarios. Scenario 1. The atmospheric annihilation. Picture this: a colossal chunk of ice and rock, perhaps several kilometers across, screaming towards Earth at speeds far greater than any comet or asteroid from our own solar system, maybe 50, 70, even 100 kilometers per second. This isn't just fast, it's blindingly fast. As it slams into our atmosphere, a thin protective blanket, the air itself becomes a solid wall. The sheer kinetic energy, the energy of motion, is unimaginable. It's instantly converted into heat and light. The leading edge of the comet would glow with an intensity that would put the sun to shame, vaporizing layers of its icy surface in a process called ablation. The friction, the compression of the air in front of it, would generate a shockwave, a wall of superheated, hypercompressed plasma, hotter than the surface of the sun. This isn't a gentle entry. The comet would begin to fragment, torn apart by the immense aerodynamic stresses, like a bullet hitting water, but on a cosmic scale. Each fragment, still traveling at mind-boggling speeds, would create its own miniature inferno. If the comet were to break up high in the atmosphere, say 20 to 50 kilometers up, we might witness an airburst. Think of the Tunguska event in Siberia in 1908, or the Chelyabinsk meteor in 2013, but magnified 1,000-fold. The superheated air would explosively, creating a colossal blast wave, a wall of air powerful enough to flatten entire cities, forests and infrastructure for hundreds, even thousands of kilometers in every direction. The thermal pulse, a sudden flash of heat, could ignite widespread wildfires across continents. The atmospheric chemistry would be irrevocably altered. Vast quantities of nitrogen and oxygen would be superheated, forming nitrogen oxides that would deplete the ozone layer, allowing harmful ultraviolet radiation to flood the surface. Dust and aerosols, pulverized comet material mixed with vaporized rock from the atmosphere itself, would be injected into the stratosphere, blocking sunlight and potentially plunging the planet into a temporary, devastating impact winter. Photosynthesis would plummet, ecosystems would collapse, and the very air we breathe would be thick with the ghosts of a cosmic collision. Now, let's imagine our interstellar visitor misses land and plunges into the vast, deep embrace of the ocean. This isn't a soft landing. Even water at these speeds acts like solid rock. The impact would be instantaneous and cataclysmic. A cavity, kilometers wide and deep, would be blasted into the ocean floor, momentarily displacing an incomprehensible volume of water. The force would be so immense that it would vaporize trillions of liters of seawater, sending a titanic plume of superheated steam, pulverized rock and comet debris rocketing miles into the atmosphere, even into space. This plume would be a global spectacle, changing the very color of our sky. But the true horror would be the tsunamis, not just one, but a series of monstrous global tsunamis radiating outwards from the impact site. Imagine waves, initially hundreds of meters high near the impact, traveling across entire ocean basins at jetliner speeds, slowing only as they approach coastlines, but growing in height as the seabed shallows. These weren't ordinary tsunamis. They would be walls of water, miles high in some places, capable of inundating vast coastal regions, sweeping away cities, entire island nations, and pushing inland for hundreds of kilometers. The sheer erosive power would reshape coastlines, strip away soil, and salt agricultural land for generations. The sudden injection of massive amounts of water vapor into the atmosphere would also drastically alter weather patterns, potentially leading to extreme rainfall in some areas and prolonged droughts in others, further destabilizing global climate and ecosystems. Marine life, especially near the impact zone, would be annihilated by the shockwave, pressure changes, and subsequent changes in ocean chemistry and temperature. Scenario 3, the continental catastrophe. Finally, the most devastating scenario, our interstellar comet slams directly into a continental landmass. The impact would be beyond anything humanity has ever witnessed. The kinetic energy released would be equivalent to billions of atomic bombs detonating simultaneously. The comet would excavate a crater dozens, perhaps even 100 kilometers wide and several kilometers deep,
instantly vaporizing hundreds of cubic kilometers of crustal rock. The ground would heave and buckle, sending seismic shockwaves rippling through the entire planet, triggering magnitude 10+ earthquakes across every tectonic plate boundary. Volcanic eruptions would be stimulated globally, adding to the atmospheric chaos. Ejecta, a colossal plume of superheated rock in the comet material, would be blasted high above the atmosphere, some even escaping Earth's gravity entirely. But most of it would fall back down, raining fire across the planet. This re-entering debris would superheat the atmosphere, creating a global thermal pulse, igniting every combustible material, forests, grasslands, cities, into a worldwide inferno. Imagine the entire planet ablaze, a literal firestorm. The soot and dust from these fires, combined with the pulverized rock from the atmosphere itself, would create a perpetual night, a nuclear winter on a cosmic scale. Sunlight would be blocked for years, temperatures would plummet, and photosynthesis would cease. The chemical cocktail in the atmosphere, sulfur dioxide from vaporized rock, carbon dioxide from fires, nitrogen oxides, would lead to acid rain, ocean acidification, and a complete collapse of the global food chain. This isn't just a bad day, this is an extinction-level event, a reset button for life on Earth, mirroring the cataclysm that ended the age of the dinosaurs, but potentially far more severe due to the interstellar speed of the impactor. These scenarios, while terrifying, underscore a fundamental truth. We live in a dynamic, sometimes dangerous, but always awe-inspiring universe. We are not isolated. Our planet, our home, is part of a grand cosmic ballet, occasionally intersected by these interstellar wanderers, silent messengers from distant stars. The chances of such a devastating impact are incredibly low, thankfully, but they are not zero. And the very fact that we can conceive of these possibilities, that we can use the tools of physics, chemistry, and astronomy to understand such events, is a testament to the power of human curiosity. And that, my friends, brings us to the end of our journey through the cosmos. We started with nothing, a singularity, and watched as space and time exploded into being. We've seen the universe expand, cool, and blossom with galaxies, stars, and planets. We've grappled with the mysteries of dark matter and dark energy, the very forces that dictate the universe's destiny. We've contemplated the possibility of life beyond Earth and the incredible, improbable journey that led to our own existence here on this tiny, vibrant speck in an unfathomably vast ocean of stars. Remember this, you are made of stardust. The iron in your blood, the calcium in your bones, the carbon that forms the very backbone of your being, it was all forged in the hearts of ancient stars, scattered across the cosmos in spectacular supernovae, and eventually gathered together to form our solar system, and ultimately, you. You are literally connected to the universe in the most profound way imaginable. This journey through cosmology isn't just about distant galaxies and abstract equations. It's about understanding where we came from, where we are, and perhaps where we are going. It's about recognizing the incredible beauty, the profound mystery, and the sheer privilege of being conscious observers in this magnificent cosmic drama. Keep looking up, keep asking questions, and never stop being amazed by the universe. The adventure of discovery, my friends, never truly ends. It only just begins anew with each curious mind that dares to wonder.